goes. Okay, thanks. Thanks, Fernando, and the rest of the organizers for putting together this super nice workshop. I am very sorry I couldn't be there in person. I was looking forward to it. I arrived in Madrid, and then on Monday morning, I tested positive for COVID. So unfortunately, I cannot be with you there. But let's see. I hope we can convey some of the interesting stuff that I wanted to share with you online. So unfortunately, I also need to thank especially to Arun, who was super nice and agreed to change a little bit the plan of the lectures that we originally had, because on Tuesday I was not feeling so well. And actually, the changes he made are so the changes that we made on the plan they were very nice for me, but perhaps not so nice for the logical structure of the lectures. Okay. So the plan that we originally had was that Arun was going to give you an introduction to Cobordisms, then he was going to describe applications of Cobordisms in condensed matter physics, and then I would chop in, tell you how Cobordism theory has become recently very interesting for studies of anomalies, and also I will also cover like this being a works of Swampland. I will also cover the main application of Cobordisms to the Swampland literature recently, which is the Cobordism conjecture. It's also very much related to anomalies. And then in the end, we both would guide you through some computations so that you learn the tools that you can do Cobordisms yourselves. So unfortunately, what happened is because of the fact they couldn't be there. So the plan is now a bit different. So what we're doing is Arun already gave you a bit of computations. So computations are here. I'm gonna, okay, well, you see what I'm trying to do here? So it's gonna be computation. It's new iPad, so I'm still trying to figure it out. But I guess you understand. And then there's gonna be also a last lecture. So what Arun gave you was computations part 1. I'm gonna give you computations part 2. Okay, so that's gonna be tomorrow. Today we're gonna be talking about anomalies and the Cobordism conjecture. So I just want for you to keep in mind that because of this thing, there's gonna be a slightly logical change in pace. Rather than first describing what is this thing and what's important for, and then how to compute it, we were describing some of the things it was good for. Then today we're gonna, so then there were some computations, and now we're gonna describe what other things it's good for. And so, of course, also my part is online, and so that leads to a very, very important thing that I need to ask of you, which is that please, please, please ask questions. I know it's annoying. It's annoying for me as well. You guys are like sitting there, there's a screen talking to you. You're all guys are all together. So there's a huge temptation to just zone out. Please don't do that. It's very important that you ask questions. Also because I cannot see you. So otherwise it's very difficult for me to see if I'm being boring or fun or if the message is getting across. Okay, so it's very important that you guys stop me at any time, ask any questions, any comments, whatever comes to your mind, just let me hear it. Okay. Okay, so let's get started. So let's first go to describe what is the relationship between Cobordisms and anomalies. Okay, so for that I need to tell you what is an anomaly. The Cobordisms have been very useful in condensed matter physics to classify topological phases of matter, as Arun was describing yesterday. And basically, the whole point is that there's a new paradigm of phases of matter, which are described in terms of invertible TQFTs, and those are naturally classified by Cobordism. So the point is that with anomalies, something like that happens. Anomalies are also classified by invertible TQFTs, and so that's why they are naturally they have nothing to do with Cobordism. So basically the idea is invertible TQFT. This is good for condensed matter. So things like the topological insulator or superconductor. And it's also good for anomalies. And this thing physically classified by Cobordism. Okay, so what is an anomaly? So definition, or rough definition, anomaly. Anomaly, it's a phenomenon by which when you have a symmetry of a classical system, that is not preserved by quantization. So what does it mean precisely? Well, so let me just okay. Sorry, I had some trouble with the lectures, and I need to. This is not displaying correctly on my computer. Okay. So the symmetry of a classical system that is not preserved by quantization. What do we mean by that? Well, so suppose that suppose you have some classical system. So the simplest case that Diana was describing yesterday on the first day was when you have some conserved current, classically, and then suppose that quantum mechanically this thing is no longer zero as an operator equation in quantum mechanics. So how does this kind of thing happen? Well, typically, the way we understand anomalies is because in classically you get things like conservation equations from equations of motion. And quantum mechanically, you get operator equations from a path integral, from a partition function for a path integral, which is of the form Person field phi. Okay, so what can happen very roughly is that here is the classical action, captures classical physics. The equations of motion coming from that action are invariant of some symmetry, so they give you some conserved current. But then what can happen is that the measure of the path integral, okay, there's some Jacobian factor coming from the measure, which is not invariant of the symmetry. And so when something like that happens, then you do not have a conserved current at the quantum level. Okay, so what is the modern way that we describe anomalies? Well, Irene told you on the first day that whenever you have a symmetry, okay, what we can do is we can go to this path integral and add it. When we have a symmetry, at least at the classical level, we can add a term like this to the action, okay, where A is a connection on a principal G bundle. The physics is called a background gauge field. Okay, so the idea is that you have some symmetry. This current is some symmetry group G, and then you can couple the current to a background connection. You can just choose whatever background connection you want and compute the partition function here, which is now a function of anything you had before, like the metric, but now it's also a function of this background connection A. Okay, and the fact that the current is conserved, if the current was exactly conserved, what that would mean is that Z of A is Z of A plus the lambda for any lambda. So here I'm doing the abelian case for simplicity, but it's true more generally. So the fact that the current is conserved, what it means is that the partition function is gauge invariant. So current conserved is the same as partition function being invariant. Okay, and conversely, what we can say is that one way of diagnosing that there is an anomaly is that the partition function is not invariant under gauge transformations, which is another way of saying. So another way of saying this is that so if C of A is different from C of A plus D lambda, then we can say that there is an anomaly at the quantum level if the current is preserved classically. Now, another way of saying this is that the phase of the, let me see. Another way of saying is that the phase of the part of the partition of the, hold on. Okay, sorry. So we have, right, so when this thing is not conserved, you can say there's an anomaly. So another way of saying this is that in the case where the symmetry is exact, the partition function is a function of the background current. When it's not, it's something like a multi-valued function of the background current. So different gauge copies of the same connection give you different values of the partition function. So that's like saying that there's that the partition function is multi-valued. Or in mathematical language, to say when there's an anomaly, the partition function is not a function, but a section of some bundle over the space of connection. Okay, so if I draw the space of all possible connections and I have some point, if I go in some closed loop that goes back to the same point, it could be that the value of the partition function changes, and that means that there's an anomaly. So here's the space of all A's, and there's basically two cases. There's basically two big cases, which one needs to study, which are the case where
sorry, Miguel, can I ask something?
Yes, please. Please.
So the way you have written things down seems that the path depends on the gauge. So is this path in the space of connections modulo gauge? Or...
Yes, very good. Yes, that's exactly how I'm thinking about it. Okay, so I'm right. So the point is that the anomaly is that the partition function is not gauge invariant. So one way to define this is to say that if I one way to express this is to say that if I have a space of connections, and by space of connections, of course, I mean physical connections, or also modulo gauge transformations, right? Like a connection, like gauge transformation is just changing the trivialization of the connection, so it's not really changing the connection physically. So one way of encoding that there's an anomaly is to say that it's a multi-valued thing. So when you go around in a closed loop in the space of connections, you can get different values for the connection. So here, indeed, so what I'm thinking here is that I have some path in configuration space, parameterized by some coordinate t, and I'm picking some connection a of t that depends on the parameter. So I start with some value a0, and what I have is something like this. Okay. I'm identifying these 2 points. I'm identifying in the space of connections. I'm identifying the initial point and the final point, right? But if the value of the partition function is not the same, then I say there's an anomaly. Is that clear? Did I answer your question?
Yes.
Okay. Good. Very good. So, indeed. So that's the way we describe this connection. And there's basically 2 cases to consider depending on how this path looks like. Okay. So it could be that the case 1, that the path can be smoothly the form to the identity, to the trivial path. And this is what we call a local anomaly. Because in the end, the anomaly is one is gonna be able to describe in terms of local invariance. And the second case is when the path in the space of connection cannot be the form to the trivial path, to the identity. And this is what we're going to call a global anomaly. Okay, so local anomalies from the point of view of the physics literature have been understood since the 80s, and also a certain form of global anomalies. So what I really want to tell you, where the Cobordism description really enters, is when one tries to understand how to combine the recent developments in the theory of anomalies with things like topology change in space-time. Okay, so what I've given so far is a very abstract, very general description of what is an anomaly. Okay, it's very general. So for instance, you could take the I was putting here a U1 gauge field, but it applies to also anomalies of discrete symmetries or anomalies of higher form fields. Now to make the whole discussion a bit more concrete, I am gonna particularize this to the discussion to a setup which is very relevant to particle physics and to string theory, which is anomalies of free Fermion systems. What do I mean by anomaly of a free Fermion system? Well, when you have whenever you have a Lagrangian theory, you can describe in terms of a Lagrangian. There can be several fields in the theory, and there can also be some fermions, which are described by generally speaking, in general terms, by an action like the Dirac operator, where this Dirac operator is just the ordinary operator also coupled to a connection. Very good. So then, this is a system where typically one gets an anomaly. Okay, so get the anomalies typically happen for chiral fields, and one setup where you typically get an anomalies for systems like this of chiral fermions. Let me. Okay. For systems, so you typically get an anomaly for systems of chiral fermions like this one. Very good. So the whole point is that for systems like this one, I'm sorry, I have some trouble with my lectures. Okay. Okay, one has a system of when one has a system of free fermions like this, they can typically have an anomaly. So the partition function depends on it's not a function on the space of connections. And what one can do, the nice thing about systems like this, okay, is that we have a formula, an exact formula for the anomaly. Okay, this was worked out for by Diane Fried, and it goes under the name of what is called the Dye-Fried theorem. Okay, so what I'm telling you is that for this system, for this kind of systems, there's an exact formula that allows you to compute the anomaly. How does this work? Well, remember, I told you that an anomaly is associated to a particular path in the space of connections, like this. Okay. And so to understand the anomaly means that we are able to compute what is the change of the path integral as we go around a path. So anomaly equals change of path integral around the path.
Sorry, Miguel.
Please.
Can you say a word about what do you get after gauging? Because I don't think the math audience is very familiar with gauging. So if you could say what do you get after gauging? I mean, Lagrangian or something.
Very good question. So I haven't gauged anything yet.
Okay.
Okay. So I am just coupling the matter fields to some background connection. But indeed, an important reason why we care so much about anomalies from the point of view of particle physics is that they give us interesting constraints. Okay, they can give constraints for the field theory, because eventually often it's often the case that we want to gauge the symmetries. So gauging a symmetry, what it means is that on top of, we have this path integral with this partition function, which I define as some path integral of fields, blah, 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 and depends on A. And what we want to do often in physics is we want to consider actually a different path integral where we actually are also summing our connections. So what we do is something like d of A, z of A. Okay. So if you want to do something like this, this happens all the time in, for instance, when you study very simple theories like electrodynamics, it has an action of this form. It has a path integral. You also make over the background gauge field, you make the connection dynamical. If you want to gauge, there can be no anomalies. So that's why in physics we often care about the particular case where we care a lot about the particular case where the anomaly vanishes. Okay, and people talk about anomaly cancellation conditions. The whole idea is that you're looking at a particular theory and there's some symmetry, and you maybe want to gauge it. Maybe you want to gauge it because you think that's going to produce interesting dynamics, or from the point of view of quantum gravity that I didn't explain on Monday, you want to gauge it because you know you cannot break it, and symmetries in quantum gravity have to be gauged or broken. I'll be describing examples of this later on. But the idea is that if you want to gauge the symmetry, there can be no anomalies. Okay. Good. So the anomaly, what you need to understand is how the partition function changes when you're given a path in the pathing, when you're given a pathing configuration space of connections. So the path in the configuration space of connections, as I was describing before, is some path like this. And you can draw a path like this if you want in a construction called the mapping torus. Okay, so the theory that we're considering, we're doing the path integral, we're computing this partition function and everything in some manifold n. Okay, typically we consider Rn, but we consider more general manifolds. And so one can take the product of n times an interval parameterized based on coordinate t, and then you can consider, you know, you can put this connection, AT is a connection for this space. You can put it there. And so you end up having, if the manifold D has D dimensions, you end up having an MD plus 1 dimensional space with connection. Okay. So the prescription, there's the prescription to compute the anomaly of any free fermion system. Okay. In a setup like this is to is the following: the anomaly associated to the connection AT on the manifold D. Oh, sorry, let me put it like this. The anomaly is meaning the change of the path integral. Okay. So let me put it like this: the path integral of E of D plus D lambda over Z of A is actually just a phase This is not true in general. There can be anomalies which are not phases, but for a particular case of free fermion system, it's always a phase. And this phase is basically given by pi/2 times something called the eta invariant of AT, of the connection AT on the background M for a certain Dirac operator. So what is this eta invariant? This eta invariant is an object which is familiar from the mathematical literature. So the eta invariant here is a regularized sum of eigenvalues of a Dirac operator. It is not the same Dirac operator that we have in the Lagrangian here. It's a slightly different one, is related to it in a very straightforward procedure. But really, so let me just put the exact definition. So the eta invariant is this thing. Okay. So the bottom line is, if you want to compute the anomaly, okay, along any path, what you do for a system of free fermions is conceptually very simple. Conceptually, you just go construct this connection AT. There is a Dirac operator coupled to this connection, which is in a certain representation. The representation in which it is depends on the representation on which these fermions transform, but there's very simple rules for you to decide how it goes. And once you have this Dirac operator on this d plus one dimensional manifold, you diagonalize it, and you compute this regularized sum of eigenvalues, and this is giving you the anomaly. Okay. So abstractly, this is all there is to computing anomalies of free fermion systems. You just compute it and vary. And of course, the rest, the rest of the talk for the next half hour is about how to compute this guy. Which is actually, as you can imagine, quite complicated in some examples. But there's beautiful theory that that helps us compute this. So before I go on, I gave you the basic high-level idea of what an anomaly is and how you compute it in systems of free fermions. Are there any questions so far?
Yeah, I have a question. So in your original, in the first part, you introduced you introduced connections for gauging, and in this, I didn't get it if the connections in the free fermion systems are part of the fields or appear after gauging.
Very good. Okay, so let me clarify that a little bit. So the way I introduced the connection here, okay, is not for it's not gauge. It's what in physics literature you call a background gauge field. Okay, so here I just have some path integral with some fermions, which are the fields in the path integral, these guys, and I'm going to introduce the A as a source. Okay, it's just an external field that I get to choose. I get to choose an exact profile, and I just compute this thing. Okay, I add this term of the to the action, and I compute the partition function like that. Okay, and that is the partition function as a function of the background gauge field. If I want to gauge this, then I need to do a second step. So this partition function is not the partition function of any gauge theory. It's just an observable that you can compute for a theory with a global symmetry. If you have, or something which looks like a global symmetry modular anomalies.
My question, my question is, how do connections appear in the free fermion system? Are they fields, or they appear after some procedure?
You just introduce them by hand, right? So the point is that you can always so if you just have so suppose there's a global symmetry. So the original Lagrangian is something like this, okay? And then you just introduce a term like that. You can do this, right? You modify, and this is not a field in the sense that it doesn't fluctuate, but you get to choose its position precisely.
I guess, I mean, it's like a probe. It probes the anomaly. It makes you see the anomaly. If the symmetry is global, introducing this A, even if you don't sum over it, on the configuration, makes you see the anomaly. Then if you want to gauge, you have to sum in the particular.
That is exactly right. That is exactly right. Thank you. Any other question?
So,
Yeah.
so just to see if I understand correctly, so what you're saying is that if I quantize it, okay, I get a Hilbert space, and I get a Hilbert space at every point of the modelized space of the theory. And you're saying that the existence of an anomaly means that this bundle of Hilbert spaces is not trivial. Is that correct?
That is exactly right. That is exactly what the anomaly is. So in this particular case of free Fermion systems, I can be even more precise, because the anomaly, one can prove, I didn't give you the proof, but one can prove that for Fermion systems, the anomaly is always a phase. Really, what you have is the anomaly, the partition function is a function of a complex line bundle over the space of connections. Because it's just a phase. So it's the section of a line bundle over the space of connections. And what we are trying to characterize is that line bundle. Any other questions?
Yes, Miguel, are you allowing for topology change in the mapping torus?
Very good. That's coming up next. Not yet. Not yet. You're a modern person, Edu. This is. I'm still in the 80s. This is still a discussion from the 80s. Okay. Okay. Very good.
So when are the Cobordism coming?
The Cobordisms are coming after the 80s, Fernando. So in the 80s, Cobordism was just mathematics, I guess. Except for a couple of papers by Witten. And now they're more mainstream, but they're coming pretty soon. Okay. Yeah. Okay. So how do we compute this guy? Well, you have this mapping torus right here. You want to compute the phase of the path integral on this mapping torus, right? Well, and you have this eta invariant thing. Now, this is something that to physicists won't be very familiar, but it's, I think, a very important result of mathematics, which is the Aps Index Theorem. So there's something called the Aps Index Theorem. Okay. So the Aps Index Theorem, it turns out that this eta invariant I'm describing was, of course, not introduced for the first time to describe anomalies. It was introduced actually by Atiyah, Patodi, and Singer as a boundary correction to the index theorem. Okay. So we have a manifold. Let me call this mapping torus, okay, MP D+1, to emphasize that this is a D+1 dimensional mapping torus. And suppose that we have that the MP D+1 mapping torus, imagine it's the boundary of some D+2 manifold. And I think you can see, Fernando, where the coverdisms are starting to appear, right? So it turns out that this eta invariant is actually the correction you need to add to the index theorem if you want to have an index theorem for the manifold BD+2, which is a manifold with boundary. In general, when you have a manifold with boundary, you need to impose certain boundary conditions on a Dirac operator. So this is BD+2, and this is MP+1. So when you want to describe, if you want to compute things like the index of a Dirac operator on an open manifold, the index is just the difference of eigenvalues. you need to impose certain boundary conditions, and then the usual index theorem, which would be something like the index is related to what is called the index density. This is a polynomial characteristic classes, so on and so forth. It's actually corrected by a term which is precisely the eta invariant. So from the point of view of anomalies, we can do it the other way. We can say, whenever the mapping torus is the boundary of something else, to compute the anomaly becomes easy because we just need to compute this guy. Okay. In particular, one case where the mapping torus is always the boundary of something else is when the anomaly is local. Anomaly is local. Remember, anomaly is local means that the path that we have in configuration space can be contracted to a point. So what that means is that mapping torus of D plus 1, okay, is actually the boundary of just the manifold MD we started with times a disk. The disk has a boundary, which is the circle, and that's the mapping torus. And because, so if I'm drawing that disk here, and I'm putting the connection AT here, precisely because the connection can be smoothly contracted to a point, this thing can be filled in with some particular connection, and we can do it like that. So the anomaly is local, and you end up with a formula for the local anomaly, for a local anomaly, which is that local anomaly is basically I'm just being a bit cavalier here, but basically, if you want to compute any local anomaly, what you need to look is not just at the anomaly theorem one dimension more. You need to look at some polynomial in D plus 2 dimensions. This thing, and then you need to somewhere all fermions of the theory, you have several. This thing is the anomaly polynomial from the 80s. Okay, so that's the old anomaly polynomial. This is how, from this modern point of view, using D time variant, you recover the old anomalies from the 80s. In particular, if you want to cancel anomalies, if you want to say there's no local anomalies, well, it has to be true that the integral of this anomaly polynomial or over any D plus 2 manifold has to vanish. Okay, so no local anomalies means vanishing anomaly polynomial. Okay, and so you recover the old result from the 80s. It just comes from the Aps Index Theorem at this point. Okay. Any questions about this?
Yeah. Is it just a reformulation of the descent procedure, the Storazumine? Or...
Yeah, absolutely. From that, if this was all there was to it, this would be stupid. It would be a waste of time, right? The whole point is that this formalism uniformly captures local anomalies and global anomalies, as I'm going to explain now. Okay. And global anomalies you cannot capture from the descent procedure, right?
Can you say again what is the sum? The sum is over what? Over Fermion?
Right. So I was a bit cavalier here. Okay. So here's the thing. So when you have typically in physical theories, you have. I was writing an action above. I was writing an action which was integral of psi bar d psi. Okay. But typically in physical theories, you don't have a term like this. You have something like Fermion 1 plus Fermion 2, which are possibly in different representations of the global symmetry and so on and so forth. You have to add many of these things. Now, you can always rewrite this as some big Fermion D transforming some big reducible representation of the symmetry, okay? And then the procedure I explained works by taking this Dirac operator to be the Dirac operator you need to use. But very often in physics, we like to decompose things into reducible representations, and then we have one fermion and another fermion. And then what I'm telling you is that this thing is linear. You're first doing for one fermion, for another, and then you add up, and you compute the total anomaly. Okay?
What's the anomaly polynomial or polynomial in? Like, what's the variable of the polynomial? And also, can it be interpreted as what is the variable of the polynomial that it's supposed to be a polynomial in? The anomaly polynomial.
What is the degree of the polynomial?
The variable.
You said
the variable.
Oh, the variable. Oh, very good. Oh, so okay. So right. So it depends on it basically is the index density that appears in the Atiyah-Singer index theorem. So remember our variables that we've been having since we started. We had two variables in general: a connection A and a metric G, which originally I defined on my manifold M, and then I extended to the mapping torus, and now I also extended to this manifold BD plus 2. So this manifold BD plus 2 has both a connection and a metric. The connection has a Chern character, and the metric has curvature, and you can define a Pontryagin class for it. Okay, so it's just basically a polyform of the characteristic classes. of the connection and the metric. This is just so these two guys are characteristic classes. They are genus. This is the A-roof genus as the ones that Weber is describing in his talks. So we just have the term character and the A-roof genus of the metric. Did I answer your question?
Yeah.
Okay.
Can it be interpreted as the curvature of some connection on the bundle of Hilbert spaces?
That's a great question. I don't know the answer. I think well, okay. So in a sense, yes, that's where we are quantifying. But if you're asking me to make it more precise than that, I don't think I can. I mean, on an abstract way, certainly we're doing. If you ask me what is the expression for that curvature, I'm not so sure. Okay, I think it's basically this, but yeah. Okay. Very good.
Miguel, sorry. I think I lost one step. So before you said that eta was equal to index minus this integral.
Yeah.
And now you say eta is equal to that integral. So.
Oh, sorry. Because so you see, you're completely right, Rafael. I was there's a minus. Yes, absolutely.
No, but
I just been a bit cavalier because.
No, what about the index part? So I'm a little bit.
Oh, I'm sorry. Oh, okay, sorry. Let me. Yes, I was a bit too quick. Okay, you're completely right. Okay, so you see, the anomaly is a phase. Okay, and the eta invariant is basically this phase. So if I right. So what I want to compute is this thing, but I only care on this thing modulo an integer. You see what I mean? The anomaly, the actual anomaly is the exponential of this guy. Okay.
Yeah. Okay.
And so the index is, that's a very good question, which I shall explain. Apologies. The index is an integer. Is the number of eigenvalues with one character minus the number of eigenvalues with the other character. So it doesn't matter. So I can trade one for the other.
Okay. Thanks.
Okay, great. Okay, so now what happens when I have global anomalies? And just to, you can make the discussion more general and a bit more complicated, but just to simplify my life and make things easy, okay? Let's just say that we are looking at cases when local anomalies cancel. What is global anomaly? Well, global anomaly means you look at a mapping torus for a transformation and you cannot smoothly deform to the identity. And in general, the mapping torus for a global anomaly is not the boundary of some d plus 2 dimensional manifold. Before I could construct it explicitly, now I cannot. Okay. So in general, it's in fact true that there's no such thing. Okay. So what that means is that you cannot compute the anomaly using the Aps Index Theorem. Okay. But there's something very interesting that happens again because of the Aps Index Theorem. Suppose that this mapping torus is cobordant to some other n+1 manifold x n+1. Suppose I have something like this. Okay. Suppose there's a Cobordism between these two guys. Now, the Aps Index Theorem is going to tell you that the eta invariant on the mapping torus minus the eta invariant on xd plus 1 is going to be equal to the index, which I'm going to ignore as in Rafael's previous question, plus the index density. But I'm assuming that local anomalies cancel. I told you I was assuming that. So this thing disappears. So what did we conclude? What we concluded is that the anomaly, this thing, the eta invariant, the anomaly, is a Cobordism invariant. And this is the basic reason why Cobordisms are so useful for the study of global anomalies. Okay. As you've heard several times in this set of lectures now, Cobordisms are abelian groups And in every setup that I know that is interesting for physics, they're finally generated.
Wait, Miguel, this is the 8 invariant mod 1, right?
Sorry?
Oh, this is the 8 invariant mod 1 because we still have the index.
Yeah, that's right. It's a Cobordism invariant eta mod 1. That's exactly right. But that's all I care for the anomaly, okay? So this is actually great news, because that means, for instance, if I want to compute an anomaly, I just need to look at the at what the eta invariant is for the generators of Cobordism group. And if I can compute it just there, which is, it's difficult enough, but at least I've solved the problem of understanding all possible global anomalies to a finite set of cases. If you can compute the eta invariant of the generators of the Cobordism group, then you get, then in principle, you get all possible anomalies. You actually get a bit more than that, because from what I've been telling you, you don't really need that eta of any manifold. For instance, suppose that one is actually, suppose that you want to gauge symmetry. Suppose I want to gauge symmetry, gauge the symmetry eventually. So as I told you before, that means that the anomaly, I want the anomaly to cancel. Anomaly must vanish. Then really what I need to impose is that the anomaly A on, not on any manifold, just a mapping torus. So in D+1. So that means manifolds of the form M times a circle with a certain connection vanishes. If it doesn't vanish in more general cases of manifolds, then in principle, I don't care, okay? And so you need to impose the anomaly on a mapping torus vanishes, okay? Now, what I just described you up to now, this is the 80s, okay? I've introduced the description in terms of Cobordism, which was not pervasive in the 80s, okay? I explained this in relation to Cobordism theory. But physically, this is just all the anomalies of the 80s, okay? So when people were studying anomalies, they would impose this kind of thing. They would then use Cobordism theory to find all possible mapping tori. If they look at simple enough cases, they could actually guess it by hand, and they would just impose the anomaly vanishes for all cases. But we've learned a little bit since the 80s, and recently we've learned that there's a stronger condition that we need to impose whenever the underlying physical theory, and this is related to Eduardo's point before, admits or has topology changing process. Now, when you say topology change, people immediately think quantum gravity, and that's right. And I will be describing in the lecture after the break a bit more why do we believe there's topology change in quantum gravity. But it doesn't have to be like that. It doesn't have to be quantum gravity story. There are many theories for which you admit topology change, okay? If you have some condensed matter material, it might just be because you can give it different shapes and you can glue them and cut them. Or if you want a more stringy perspective, if you consider the theory of a D3, let's say a D3 brane on flat space, it's just some brane floating on space. And suppose that this is in 10-dimensional space, so we're not gonna do anything fancy with topology of space-time. Still, the warp volume of the D3 brane can grow handles. That's a thing. That's a thing that can happen. I hope you enjoyed my very accurate portrayal of a handle. Apologies for that. But this is something that can happen. So you can have topology change in quantum gravity, and when in quantum gravity, but also in field theory. And
but sorry, Miguel, what is this in field theory? Your handle in field theory? What is that?
Sorry, what? Sorry, what is
your handle in field theory? which kind of physics is this creating a handle for the liquid brain?
Well, it's something like what I'm saying is that when you describe the word volume theory of a liquid brain, the topology, the manifold in which you describe that field theory can change topology, and that's not a quantum gravity process. It's just that the brain can recombine. Okay, this is not a process you describe in terms of the Yang-Mills fields, but it's just something that you can do. It's like summing over washes in string theory. Okay.
Okay.
It's not going to be a dynamical process, certainly. It's a very off-shell process, but you care for those for anomalies because remember the basic picture I always drew. This is the space of connections, okay? And we are going on closed loops on the space of connections. Well, imagine that no allowed topology change. Then I can also go on closed loops in the space of connections in which I change not only the connection, but I also change the topology. Okay, that's something I'm allowed to do now. In particular, look at the mapping torus I drew before. Before I drew the mapping torus, so this is M, MD, MD, and then I would put just a circle here, an interval, and then I would glue the two things together to produce a circle. If I have topology change, I can do these things. I can introduce a hole here, which corresponds to, nucleation of a baby universe, if you want, from the point of view of the word volume theory. But it's just the topology is fluctuating, okay? So maybe something like I drew here corresponds to a process where the D3 brain grows a handle, and then the handle disappears. Because of course I need to go back to the original configuration, but you can do it like that. So topology change gives you additional closed paths in configuration space, which means it gives you additional anomalies. Okay, this is the basic physical idea, and this is going to happen whenever you have quantum gravity, or also when you have topology change like this. And these new anomalies, okay, what they amount to, if you're allowed to put holes here in whatever way you prefer and handles and stuff, in the end, what it amounts to is that this condition that we have that the anomaly must vanish in mapping tori. Let me see, because there's some lag here. So this condition that anomaly vanishes in mapping tori, it's improved to the condition, if you have topology change, that the anomaly vanishes for any manifold, for any Cobordism class. Okay, so this improved anomaly cancellation condition is what we call the vanishing of die-free anomalies. And this is exciting because it gives you new things. It gives you new consistency conditions that you didn't have before. Okay, now there's there's a couple of them that we might describe in a bit more detail in the lecture about computations tomorrow, because of course I haven't told you how to compute any of these things, but just to tell you briefly, okay, there's just to give you an example of how this can lead to interesting physical constraints. And by the way, let me emphasize that in the case, if you have some additional information, like that you're talking about the volume theory of a deep brain or whatever, sometimes, as I described, you can talk about this anomaly cancellation condition without invoking gravity. But if you just don't know anything, you can always apply it in a theory of gravity because gravity has topology change. So in other words, this thing is a Swampland constraint. It's something that happens because you have topology change in quantum gravity. So just to give you an example of something that this kind of thing can lead to. So there's, for instance, an asymmetry that in the standard model that has been proposed. So in the MSSM, in the supersymmetric version of the standard model, you often generate operators that mediate what we call proton decay. Those would have the operators that you write on in effective field theory would cause the protons to decay. And we have observed that proton is a very long-lived particle. So they would be in contradiction with experiments. So people, in particular, Luis and Ross, the Ibanez and Ross, they propose a Z3 symmetry, a 3C symmetry, a discrete symmetry, okay, that which is called proton triality. That if you impose forbids precisely the dangerous operators that will cause the proton to decay. Now, you know, in quantum gravity, as Irene told us the other day, symmetries are either gauge or broken. And we want the symmetry to be there, okay? So that it's, because let's say that we want to say that, no, we want this to be a good symmetry so that it actually protects proton decay. So the symmetry is not broken, so it has to be gauged. But if it has to be gauged, it has to be anomaly free. So what does it mean that it's anomaly free? Well, it means that the anomalies cancel. And Ibanez and Ross studied those, and there's many anomaly cancellation conditions involving mixed anomalies within an abelian gauge fields or whatever. But in particular, there is an anomaly involving just this C3 field with itself. Okay, so if for this particular case you look at the anomaly which only involves the C3 field with itself, it's classified by a Cobordism group. Okay. First of all, we have Fermion, so it's a spin Cobordism group. Standard model lives in 4 dimensions, and this anomaly theory lives in D+1 dimensions. So we need to look at the 5-dimensional Cobordism group. And we have a C3 gauge field, and that's denoted like this. And this Cobordism group happens to be Z9. Okay? We might look at the computation of this group tomorrow because it also involves calculation of eta invariant. Now, this guy, this Z9, not every class in the Z9, each of the classes here correspond to different spaces with different bundles. So mapping tori only exists for 3 times the class of the generator. Okay, so if you look at traditional anomalies, traditional anomaly is just 3 times the anomaly of the generator. Okay, so the anomaly of the generator class of the C9. Now, you can actually compute what the anomaly for the generator is for the standard model, and anomaly for generator is 1/3 actually. And remember, the anomaly is defined modulo 1. So the traditional anomaly for the pure anomaly, there are mixed anomalies that do not vanish, okay? But let me not talk about those. Traditional anomaly vanishes. But the Diefried anomaly does not vanish. And so the anomaly for one generator, so this is the anomaly for one generation of fermions. So for our mathematician friends, there is this phenomenon that when you look at the particle spectrum that comes in the standard model, it seems there's a pattern that repeats itself. The representations of every field under a global symmetry, under the gauge symmetry of the standard model, the particles arrange themselves into multiplets that repeat themselves. And each of these multiplets we call a generation. So when I say that the anomaly is 1/3, I mean the anomaly for one generation. So vanishing of Diefried anomalies for this particular case implies that the number of generations, so that if you have n generations, this is the anomaly. So the anomaly is equal to n/3. It's the anomaly times the anomaly is the number of generations times the anomaly of one generation. And we want this to be 0 modulo 1, which means that n is a multiple of 3. And experimentally, we've seen in the real world that k is equal to 1. So there's actually 3 generations in the real world. So precisely because we have free generations in the real world, this symmetry has vanishing Diephrid anomalies. Okay. Of course, let me be very clear. What I describe here is not an argument that if this symmetry is stable, well, it's an argument that if this symmetry exists and is exact, the number of generations has to be a multiple of 3. But there's many other ways in which you could try to solve the problem with Proton stability. So just to be clear, it's just a nice scenario. It's not something which is rock solid. Okay. But I just wanted to give you an example, very simple, down to earth, not connected to string theory, standard model example, where these anomalies, these new Diephrid anomalies tell you something new, because my basic aim here is not so much in this lecture to give you all the details for everything, is to make you excited about it. It's to try and convince you that this is a very interesting thing and perhaps something you'd like to look into in the future. But I think I've used up all my time for now. I think you guys are going out for coffee, and afterwards we'll come back with applications of cobordism to quantum gravity, so something like the Cobordism conjecture. And if time permits, we will unify what I've described now with the Cobordism conjecture. Basically, you can use the Cobordism conjecture to extend the notion of Diephrid anomalies even further, and to provide genuine swampline constraints on theories of gravity, which can actually become very powerful. So I think I'll stop now and take any questions you might have. Thank you.
Thank you. Questions? Wow, no coffee. Okay, speak up or we use the mic. Laurent?
So you said that you didn't need quantum gravity to have these topology changes. Do you have an actual example for, let's say, n=4, super Young, something like purely bottom up?
An example for like n=4 super Young-Mills.
You have these topology changes without needing to invoke string theory, for instance.
Yes. Oh yeah. Well, I mean, you mean examples in string theory? Yeah. What I drew here is an example. Like you can certainly describe a path in configuration space for a D3 brane where it grows a handle and the handle disappears. That's certainly something you can look at. And in fact, for the particular case of the D3 brane, something interesting happens. So yeah, for instance,
you're invoking a D3.
Yeah.
Can you do it just with the usual content of n=4 super Young-Mills or for Wilson lines or something like this?
Well, you can certainly compute these anomalies. I don't think in that case you have in that case you do not have an argument that they have to vanish. Okay, so certainly you can compute still this thing, and an interpretation for it would be, if I put the theory in this mapping tutorial with topology change, here's what the anomaly is. You wouldn't have an argument if there's no argument that you can do topology change that the anomalies have to vanish. And indeed, we have field theory examples where they don't vanish. Okay. So for instance, there's a symmetry for the world of the D3 brane where something like this happens. Okay, there's a topology in transition. You can compute the anomaly like this. It's the duality symmetry of n=4 per Young-Mills, but that duality symmetry is a global symmetry. It's not a gauge symmetry. So that means it can have an anomaly. Anomalies do not need to cancel, and indeed you can compute this anomaly, and it doesn't vanish. And actually, you might be familiar that when you have anomalies in field theory like this, you can match them to the topological terms of the holographic dual. This is also true for this more general notion of anomalies, for these Diephrid anomalies. And in this particular case, we found the topological term that matches this anomaly. So yeah, the whole story, you can if you don't have a brane interpretation of it or anything, you can still just play the game, and they can still be useful. So for instance, you can also all these anomalies, for instance, for a global, if you have them for a global symmetry, that you can do things like Toft anomaly matching and all of that, and it still works. It's just perhaps not the focus that I have in mind so much, because this being a swampline workshop, I care more about what happens when you break symmetries or when you have to gauge them than when you have them exactly. But of course, for the field theory setup, that's a very interesting question.
So a related question, Miguel.
Last one, and then we go for coffee.
Sorry,
And whoever wants to make more questions, Miguel is in here confined, so he can't escape.
So imagine the standard model had a gauge type-free anomaly that you cannot cure. Could this mean that the quantum gravity is not the theory of the universe?
So, say that again. So the standard model has an anomaly?
That the standard model had a type-free anomaly, that gauge that you cannot cure. Could this rule out gravity?
No, I mean, we've been in that situation actually before, right? So for instance, as for some period of time in the 90s, right? People discovered the top quark, anomalies were not canceling in the standard model. So then people were predicting the top quark. So
that you couldn't cancel. I mean, that you couldn't cancel it. You know that
there's no anomaly I know that you cannot cancel by adding more crap. So I would predict extra.
Okay, but my question is, if it was like that, you know, we knew nature had this anomaly, which is it's only there if you allow for topology change. Would it mean something about the universe?
Oh, okay. So you're telling me, suppose there is a type-free anomaly that there's no way you can cancel, which already I think is impossible. I think they can always be canceled.
Okay, but never mind.
But with usual anomalies, you give up gauge invariance.
Right.
Worst case scenario. So there should be something like this in here too.
Well, yeah, no, that's what Edu is saying. Maybe what one ends up concluding is that the topology change one has in quantum gravity is restricted. Maybe the paths there's one thing that is true. I certainly just assumed, because I wanted to, that any topology change, that the most general possible topology change process is possible to give me these anomalies. Maybe that is not true. Maybe there's restricted paths one needs to consider, in which case that would lower the number of constraints. It is very difficult, Edu, so something like that could happen in principle, but it's very difficult once you have that to make things consistent with cutting and pasting, you know, because if you want to exclude, for instance, the process that has 3 holes, I can certainly consider a path integral, which is everything minus 1 hole, and the path integral with just 2 holes and all the other thing is preparing a quantum state here. This is other thing is also computing a quantum state on the other side, and then the path integral we're computing here is just computing the overlap between these 2 states. So it's very difficult to put restrictions like however you like on the topology. But I don't think there is a proof that you cannot do something like this. And in a case like the one you've described, I guess that would be the conclusion, that maybe there are some paths in topology changing process that somehow are not possible, and that's it. However, well, as I said, it would be difficult to understand mathematically, and the premise you want to have, which is that there is a symmetry that cannot be cancelled, I don't think that's a true premise. I think it's always possible to cancel them. In fact, yeah, they're worst case scenario.
Very nice. I think the coffee is getting cold. It's very cold in here, so the coffee is getting cold.
Okay.
Let's keep talking here with the computer or when we come back. Okay. Thank you, Miguel.
Okay.